I would like to welcome to our Nature Network speaker series presentation Paul Thibault, who joined the Nature Alberta Board of Directors in September 2023 as the Southern Alberta Regional Representative. He is a longtime member of Grasslands Naturalists, serving on the board of numerous committees related to governance, finances, communications, and technology. He is currently interested in Southern Alberta irrigation issues and the effect of climate change on future water availability. He is the chair of the newly formed Grasslands and Naturalists Irrigation Committee, and Paul has given Southern Alberta conservation issues a renewed perspective for Nature Alberta activities. So, Paul, thank you for being here tonight with us, and I will turn it over to you.
Good. Well, thank you, Nick, and for the opportunity to present this topic. I'm going to go on a share screen right now. Can you all see my screen?
Showing up on my end.
Perfect. Okay. So this talk is on the Alberta irrigation expansion. It's a proposed irrigation expansion. So it'll talk about the expansion itself, the amount of water that is actually available and will be available for that expansion, and also some concerns about the environmental impact. I think the first place to go is to a letter that the Premier sent to the Minister of Agriculture and Irrigation in 2022. In that letter, there was quite a few requests, but one of them read as follows. As a lead, work with the Minister of Environment and Protected Areas to expand and improve the irrigation network within Alberta, to ensure Alberta is best served and maintains its standing as a global leader in food development and distribution. Now, that was not the first time that we've heard about irrigation expansion. It actually came up as early as 2016 when the consultant WaterSmart wrote quite a detailed report outlining in quite some detail of what that expansion might look like. I first got into this as Nick mentioned, I'm on the Nature Alberta board. I'm the Southern Alberta representative, and Claudia Lipsky is the Central Alberta representative. So our regions are roughly divided by the Red Deer River. And she mentioned that she sent me an email concerned about a proposed project in the ND of Acadian Special Areas, which is in the area of Empress near the Saskatchewan border. And she was concerned about the proposed project, and she was particularly concerned about the threatened leopard frog, which she had seen at Princess Spring. And the Princess Spring, the project intends to convert that into a reservoir. And I loved her email because it read, as it shows at the bottom of the slide, 33 frogs in 33 minutes and 33 Celsius at 30th of July 2023. Well, that got me quite intrigued. I thought it was a really good way to introduce this. And I got quite interested in this. I wrote a report of an open house, and Rick Schneider at the time, who was the editor of the magazine, asked me if I'd be interested in writing an article. And I thought maybe before writing an article, I should study it in some detail. So I guess that's exactly what I did. So I spent 1 year studying the water quantity and quality associated with irrigation in the South Saskatchewan River Basin, which includes the Thibault, Oldman, South Saskatchewan, and Red Deer rivers. That there was originally quite a long report, but from that report, the section on water quantity was extracted and formed into a separate report, and that report is now on the Nature Alberta website. And from that report, I then wrote the summary article for the summer edition of the Nature Alberta magazine, which was dedicated to water issues, and it's an issue well worth looking at because there's a lot of other great articles there on water matters. Well, when I submitted the first draft of this talk to the managing editor, uh, the managing editor is a great fairy tale enthusiast. And he noticed two plays on words here. The word frog as is leopard, northern leopard frog, and princess in Princess Spring. And reminded him of the Grimm's fairy tale, The Frog Prince. And the story goes roughly like this, is that the princess goes to a well and she has this golden ball that she really treasures. She throws it up in the air, but it accidentally falls in the well. And she's really desperate because she can't reach it. So a frog pops up and offers to rescue the ball and bring it back to her on one condition, that she brings the frog back to her place and lets the frog live with her, eat with her, sleep with her. Well, the princess was so attached to this ball that she would have promised anything, and that's what she did. And she took the ball, went back to castle thinking that everything was fine. But then the frog showed up at the castle and caused quite a commotion. And she had to confess to the king that she had made this promise to the frog that she couldn't keep. And the king said, well, promises are meant to be kept. So once she kept the promise, the frog turned into a prince, which was what he was in the beginning because he had been turned into a frog from the wicked witch. Well, it's an interesting story and it's a very clever play on words, but it's a bit more than that because it involves a promise. And as we go through the story about the irrigation expansion and even the history of irrigation, it all had to do about promises and in some ways conflicting promises. So I want to thank Jason Schwitter, the Nature Alberta magazine managing editor, for introducing this fairy tale allegory. So one thing we may want to think about, I go to one thing we may want to think about uh, is as I go through this presentation is who is who? Who's the frog, the princess, and the king, and what was a promise, or in fact, it could be what were the promises. So before going into too much detail about the irrigation expansion, I think we first need to look at where we are and where we've been in terms of water quantity. And so I'll be looking mostly at the Southern Saskatchewan River Basin. And if you look at that basin, water is allocated to the various sectors, and those are shown there. And they're shown there for the Bow, Oldman, the Lower South Saskatchewan, and the Red Deer River. The two I want to highlight are irrigation and municipal. And you can see from that table that for the Bow and the Oldman River, the main consumers by far are irrigators. After that are municipal. But in addition to that is that irrigators typically return 10% of the water to the river, whereas municipalities return 80% in the form of wastewater. So if you actually take the ratio of the net irrigation, in other words, that diverted minus that return, and you compare that to the municipal, you get a ratio at the bottom there. And the ratio is typically, well, is approximately 18 for the Bow River, and it's 125 for the Oldman River. So you can see that in terms of net values, those two rivers are by far the biggest net consumer. Now, how does that impact our rivers? Maybe the best place to look at is in Medicine Hat, where I actually live, because we get the water from both the Bow and the Oldman River. So this is a 10-year moving average of the summer average flow, starting from 2011 to it actually goes to 2023, but it's 10-year moving average. So you only go up to 5 years before on either and after on either side. So the main thing to look at here is that there's a decreasing trend in the water flow. The other thing you'll see is that there's large oscillations, and I'll talk about this just in a minute. And the other thing I'd like to mention is that we remember the droughts of 2001, 2002, where the river flows was low. We also are right now in a dry period where water flows have been low, but it's nothing compared to what it was in the 1980s for those who are old enough to remember that time where the water flows were very low. Now, if you take this curve and you compare it to what's called a natural flow, the natural flow is a flow you would get if humans weren't involved. In other words, there would be no dams, no reservoirs, no irrigation. And what you see from that is that that blue line, which is a natural flow, is a pretty constant. I mean, other than those oscillations, on the average, it hasn't changed that much compared to the recorded flow. Now, what's with all these oscillations? The oscillations are due to what's called the Pacific Decadal oscillations, and they occur on the western coast of North America. And what happens is that if you look at the red curve there, if this is a local climate phenomena, and you have oscillations where the surface water ends up being hot, warm, and then cooler, warm and cooler. So on that red curve, is uh, is when it's high is when the water is warmer. So it's described by what's called the Pacific Decadal Oscillation Index. So that index is high when the water is warm on our west coast. And what happens when that water is warm? Our water flow in the rivers is low, and 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 the same thing in the opposite directions. So there's a strong negative correlation between the annual flow and the PDO index. In other words, they are out of phase with each other. So that's the main cause for these oscillations. Now, to filter these oscillations, we can average out rather than 10-year moving average, do a 30-year moving average. Uh, what you can see here is kind of interesting because you see that downward trend, but you also see that it kind of stabilized around 1980. In other words, the by that time, the irrigation structure had pretty much been installed and things kind of stabilized. But there are still oscillations. And if you want to really filter them out, you actually need to do a 50-year moving average. And then what you get in that case is that you can see at the top that the natural flow has virtually not changed, whereas the recorded flow has dropped by about 33%. And again, that point on the far right doesn't go to 2023 because a 50-year moving average, you need to have 25 years on either side. And for the same reason, the curve does not start at 1911. So what are the main conclusions from all this? Well, in terms of water flow, we have 2/3 of the flow that we used to have. So we had 1/3 drop in recorded summer flow, let's say from June to August, from the 50-year period 1911 1960 to the recent period 1974 2023. Now, if you combine the fact that this drop is not due to climate change because the natural flow did not barely change, and it's also not due to other consumers such as municipalities because the net consumption of municipalities and other sectors is much lower than what it is for irrigation. So you can pretty much attribute that to irrigation. Uh, Now, again, these curves shows that natural and recorded flow follow an oscillatory pattern due to Pacific Decadal oscillations. I think these are really important because we should really resist the temptation to extrapolate the current trend to future flows. Whether you are a person who is a strong advocate and are really concerned about climate change, or you are a climate denier, don't use current trends to prove your point. Uh, and you can't even go 10 years back. That's not enough. As you can see, because of these oscillations, you must go much further back. So it's even hard for us to know exactly what it will be 20 years from now. It's pretty much a guess. So How does that affect the health of our rivers? The health of our rivers, you can separate it in two parts. There's the aquatic health and there's the riparian health. The health is basically determined by the water quantity and the water quality. The riparian health is the health of the vegetation along the rivers. And for us in southern Alberta, we're mostly concerned about the cottonwoods. Now, the talk is title is The Four Pillars of Water Availability. But before I get into that, I want to talk about three other pillars that are more commonly known and are actually quite relevant to this talk. And they're the environmental, social, and economic. So uh, we as humans and a society and governments governing us need to take those three pillars into account. Ideally, we would want some kind of balance between the three of them. And that's an important aspect to consider when I present some of the other results uh, on the water quantity. What are the main properties describing river quantity? There are three really important factors. There's the in-stream flow needs, the in-stream objective, and the water conservation objective. The in-stream flow need, well, that came about after the 2001-2002 drought, and I guess the 1980s where it was very dry. And there was an interest in studying how much water does the river actually need to sustain aquatic organisms and processes. Well, that was studied in some detail scientifically, and the conclusion was that typically you need 70 to 85% of the natural flow. Again, that's the flow you would get if humans were not involved. Uh, you need that to have a healthy river. The in-stream objective is kind of the other extreme. That is a minimum requirement for aquatic life. That should also be scientifically determined. Unfortunately, in many cases, it's not. For example, it's not the case for here in Medicine Hat. It's not the case for the Red Deer River. It's not the case for near the mouth of the Bow River. And this in-stream objective is used a lot in controlling dams. Now, the other one is the water conservation objective. And going back to these three pillars, that was a compromise. What happened is that if the in-stream flow needs had been applied in 2005, the allocations to the irrigators would have had to be reduced. In other words, it would have meant going back and revising very old licenses. So it was a compromise between the in-stream flow need, which is 70 to 85%, and the socioeconomic needs, the three pillars of water sustainability. So they ended up with 45% of natural flow, which is quite a bit below than in-stream flow need. Now, in the winter, the flow gets really low, and even the natural flow gets too low, especially for servicing cities and industries. So when it gets really low, there's an added criteria of 110% of the stream objective, and that comes into effect when natural flow is low. So it's the greater of these two. Now, the big caveat here, and which is affecting the rivers, especially the Oldman, the Bow, and South Saskatchewan, is that senior irrigators got their licenses well before 2025. And because of that, they were exempted from the condition of needing the 45% or meeting the WCO. And that has had a huge impact on where we are today. So how have we done with this water conservation objective? Well, going back again to Medicine Hat, which is a good indicator, again, because we receive water from both rivers. And if you can look at this plot shows the recorded percentage of the natural flow, also called portionable flow. I won't get into that. That's something that PPWB likes to call. But anyways, what's important here is that if you were at 100%, in other words, the the recorded flow would match the natural flow. That dashed line represents the 45% WCO value. As you can see, we have often dipped below this, and we tend to dip below it, not surprisingly, during the irrigation season. And it's particularly obvious, it was particularly obvious in the 1980s, in the drought years, 2001, 2, and a few years afterwards, and also recently. Now, fortunately, the situation is much better on the Red Deer River. The Red Deer River currently has very little consumption, and it has maintained its water levels well above WCO. So that is certainly good news. Now, it is currently good news, but there are projects, as I mentioned, the one on the Red Deer River and the Acadia Special Areas, which will change this. By how much, well, we'll need to see. The other thing you may ask is, what's with these big peaks? Like we're talking about situations here where the recorded flow is much higher than the natural flow. Well, that is intentional, and that is because municipalities and industry need more than a natural flow in the winter. The natural flow in the winter mostly comes from groundwater flow, and it's quite low. So the Dixon Dam was built on Red Deer River to manage the flow. And so what it does, it did two things. It helps maintaining the minimum flows above the WCO, but it also increases the water flows during the winter, which is basically needed to keep servicing cities and industry. So let's get into the proposed irrigation expansion. This map here shows where the current projects or the most important projects have been proposed. Some of these are in-stream reservoirs, and some of them are off-stream reservoirs, and some of them are much bigger than others. If we take them one by one, the Chin Reservoir is an off-stream reservoir with water being fed by the St. Mary's river system. The Snake is off-stream again from the Bow River. MD of Acadia off-stream again from the Red Deer River. Dead Horse off-stream from the Bow. But now we get to the really big ones. Earmore Reservoir from the Bow River and Ardley Reservoir from the Red Deer River. The Earmore would be like downstream, closer to the mouth of the river, of the Bow River, and the Ardley would be downstream of Red Deer. These reservoirs are as big, the same order of magnitude as the Oldman Reservoir. So these are big. They will take, those two reservoirs will take about 20 years to build. All these reservoirs have potential impacts on threatened species, and the pictures on the plot here show some of them. Just one I haven't shown here. Actually, there's one for the Belly Reservoir and that will also have an effect. That's more recent, and that's under considerable discussion right now. Now there has been no approval for any of these yet. The closest to being approved is the Chin Reservoir, and they've already submitted their environmental impact assessment. Environment protected areas have reviewed them, asked them twice to return to answer some questions, but I suspect that they are EPA and regulators and RCB are must be pretty close to making a decision on that one. These other two big ones, they're still in the feasibility studies stage. The Earmore is suspected that we will get results of that feasibility study this spring. And again, it will take a long time to build these if they're ever approved. The Chin Reservoir, this is where the reservoir is. There's a little park there. it will be totally flooded. There will be flooding of native grasslands here. Also, even the bridge will be impacted. So what are the main concerns about these reservoirs? The the first obvious question that everybody asks is that where's the water going to come from for this irrigation expansion and to fill these new or expanded reservoirs? Most of our water comes in our rivers comes from from our mountains, 90% of it. And that's mostly comes from snowmelt. Uh, Now, there's a bit of a misconception. Many people feel that most of our water comes from glaciers. That's actually not true. We only get 3% of our water from glaciers. Uh, and actually, not all of that is ice. About half of that is snow. It helps out in August because it comes a bit later. So it helps out in August because water flows are usually low in August. It also helps out during in drought years. So it's not insignificant. Sometimes it comes in quite useful. Uh, the other question is how will water availability be affected by climate change? And what will be the environmental impacts of the proposed infrastructure and how will they be addressed? Well, now we get to the title of this talk, The Four Pillars of Water Availability. Proponents of the expansion use the following arguments to support the premise that this is feasible. And I call these the four pillars of water availability. This is not what the irrigation districts, this is what I coined them. The first one is that they will say that they've underused the allocated water. In other words, they have not used all the water that's been allocated to them. And also, they've always been able to meet that 1969 master agreement on apportionment. And that's that agreement between Saskatchewan and Alberta, where Alberta must give 50% of its water, natural water to Saskatchewan. The other thing they'll say is that they've considerably increased their irrigation efficiency. And they believe that the proposed new and expanded reservoirs will address climate change. And to support that, they've done numerous calculations, hydrologic and climate change computer modeling to support their case. So let's take these pillars one at a time. The first pillar, under uses of allocated water and the master agreement. It is absolutely true that irrigators have never exceeded their yearly allocation. That can't be denied. Also, South Saskatchewan River Basin has always transferred at least 50% of its water to Saskatchewan at the confluence of the South Saskatchewan and Red Deer River. Now, some will say, well, you know, we get 70% of our water to Saskatchewan. Well, that's on the average. There are years we don't do that. And if we gave them all our allocated water in a dry year, we may not be able to do that. Let's go to the second pillar, the increase efficiency. Well, there's various ways you can increase the efficiency. One good way is to change the water delivery to the crops. So there's been a move to more efficient low pressure pivots, which are roughly 89% efficient. And there's been quite a substantial move towards that. Also, pipelines are being, canals are being converted to pipelines to reduce evaporations and seepage. And the irrigation districts have made a huge effort in decreasing the return flow to the river, including unused water. Well, that is an interesting one. It's certainly good for the irrigators. They get to use more water. It's not necessarily good for the river that doesn't get that water. But from an irrigation point of view, yes, that is a valid efficiency claim. So overall, the overall irrigation efficiency has gone up from 49% to 65% from the period 2011 to 2022. That's an increase of 33%, which is quite impressive. What's interesting, though, is that despite this increase in efficiency, The water diverted has increased by 85% over the same period. Now, why is that the case? Well, the water diversion depends on one basic thing, and that's the crop water demand. And this curve shows the correlation between the water delivered, the blue line, and the crop water demand. So irrigators are very knowledgeable people. They've been doing this for decades. So they know how to manage their crops and they know how much water they need for their crops. So this just shows that, yeah, they're managing well with what they have. But unfortunately, what they have had in the past decade or so is drier climate. And so the recent trend has been to drier climate, which has increased the crop demand. So that has overcompensated the increase in efficiency that they got. So yes, the two don't contradict each other. They're quite consistent. And to go into a bit further detail, the crop demand, the net water demand, let's say for a three-cut alfalfa, depends on the precipitation and the evapotranspiration, and more precisely, the difference between the two. And so one parameter that characterizes that is the climate moisture index, which is the difference between the precipitation and the potential evapotranspiration. And as you can see, when it goes down, the water demand goes up. Again, everything seems consistent. So let's get back to this expansion, this irrigation expansion, and get to the climate change. How does the climate change impact us? Well, it impacts us in a couple of ways and differently in different places. In the prairies where irrigation occurs, we are mainly concerned about temperature and precipitation as far as the effect of climate change, because that affects the crop water demand. In the mountains, what's important is the precipitation, mostly what we get from the snow melt, because again, we get 90% of our water from the mountains. So where we are interested here is how it affects the river flow rate, which is what needed to meet that water demand. Now, to look in the future and predict this obviously involves modeling. And to do the modeling, the first thing you have to do is to pick a scenario which basically involves determining how quickly humans will act to decrease the release of greenhouse gases. You can range, there's different categories and ways of classifying these. One of these is what's called the Shared Socioeconomic Pathways, SSP. And it ranges from SSP1, which is the most optimistic scenario, to SSP5, which is the most pessimistic. Now, let's look at how this affects temperature. This was part of the study, of this study. And if you look at the temperature and if you look at the period 2061 to 2080, compare it to the historical data 1980 to 1922, which is a solid blue line. As you go into the more pessimistic scenarios, the temperature goes up, particularly in the summer. And of course, that's going to affect evapotranspiration. Precipitation is quite different. The predictions are for the same period in the same scenarios is that we will get more water, more precipitation in the spring. On the other hand, we will get less precipitation in the summer. So in the summer, you got the bad combination of lower precipitation and higher temperature. So if you summarize this, if you look at the periods 2041, 2060, 2061, 2080, and if you look at the different scenarios, let's be very pessimistic here and go into this scenario here. Well, we're looking at increases in temperature, and these are annual temperatures of 2.9 and 4.4 degrees. That is large. 4.4 is not something that you want to see. Precipitation, we're looking at an increase of roughly 45 and 50 millimeters. What is particularly important are these numbers here, how it will affect the water demand. Increase of water demand, we're looking at a percent of increase of 33 to 61%. Now, I have to say that there's a lot of uncertainty in these type of predictions because one reason being is that precipitation remains very difficult to model. And that can be seen from the next slide here. These are the various modelers that have looked into this, and they've been done through various years. And during that time, the models have changed and improved. These are called CMIP5, or some people call them CMIP5, CMIP6. So these are different generation models. The newer generation models are the CMIP6. What was used in my study, what I did is I used Climate NA, which uses CMIP6. It happens to agree quite well with a recent study done by Environment Protected Areas, and they published a paper on this. And we both predict an increase of 2 millimeters per decade. But there are some that predict much higher values. In addition to climate change, we also need to look at how the crop mixes will vary. If you look historically, the crop mixes have changed, let's say from 1997 to 2023, particularly in the specialty crops, which have doubled. And some of these specialty crops, like potato and sugar beets, require more water. So that's another factor to consider when we look in crop water demand. So the proposed new expanded reservoirs, what are the reasons that are actually being given for them? One is irrigation expansion, which is clearly one main motivator. But the other one is water security related to climate change. Not only if we increase irrigation or the population growth, but even just to support our current situation. And it's also meant to to make sure that we meet that 50% apportionment to Saskatchewan. And the other purpose that is suggested is that some reservoirs may have dual purposes, one for storing and also for flood mitigation. What are the pros and cons of these reservoirs? Well, one of the pros is increased water availability in the summer simply by storing water. Increased water availability in drought years. Facilitate meeting that 50% water to Saskatchewan. And the other thing is reservoirs help increase winter flows and dilute effluents, which is also important. And just to further show that, I've mentioned this in the past, but I think this plot really shows this. Again, this shows the flow rates historically. And in 1983, the Dixon Dam was built. And as you can see, these minimum flows here are winter flows. As you can see, they were brought up by this Dixon Dam, and also brought up the minimum above the water conservation objectives. So from a human point of view, you have to say that's a good thing. What are the cons? Well, reservoirs may be impacted by increase in evaporation losses due to climate change. And the reason for that is that reservoirs are only good if you can fill them. For example, if you have an expanded reservoir and you can only fill them as much as you could have for the non-expanded reservoirs, all you've really done is that for the same volume, you've increased the surface area and therefore increased evaporation. So that can be certainly a negative aspect. The other thing is that infrastructure interrupts fish movements. Lake sturgeon are a very clear example, but other types of fish, the dams interfere with their motion. And also it's been shown that disturbing the natural flow cycle does add stress to the aquatic life. And there is one key paper by Iceland that shows that. New and expanded reservoirs can involve flooding of native grasslands, and that is indeed the case. for many of these reservoirs that they'll be flooding native grasslands. And in southern Alberta, we've lost a lot of our native grasslands. And that, of course, it has an impact on our wildlife, for example, bird species. And also, the strategy may not work for long multi-year drought. And you can kind of see that if you look at the historical water levels at the Oldman Reservoir. The Oldman Reservoir, like if you start from 1999 to 2017, it would cycle around every 4 to 6 years. But recently, with the drier climate, it's been cycling every year. So that kind of shows that it's kind of stressed. If you had multi-years of very severe drought, it would have problems. So we've talked about the modeling for climate change, but we probably need now to talk about the modeling for the actual flow in the rivers. Basically, that's controlled by what's called a water cycle, where you have water flowing down, rain and snow coming down over the mountains. It comes down through the streams, which feed into the rivers. And in the winter, it actually comes through the groundwater flow into the river. And 90% comes from the mountains. After it evaporates, and then you complete the cycle. How do you go about modeling that? Well, I divided this into blue and green boxes because one is how you do it and the other one is what you get out of it. You first start by assuming a climate scenario. Depends how optimistic or pessimistic, or maybe you look at multiple scenarios and compare them. And then you will feed that into what's called a global climate model, GCM. These have been developed by many countries. There's many of them. And this is where the CMIP5 and CMIP6 come into play. Unfortunately, the resolution of these models is too coarse for local predictions. So you bring these into a regional climate model, or basically you're downscaling and increasing the resolution. And from that, you get two things. You feed it into your crop water demand model. You feed the temperature, the precipitation. From that, you get the CMI and determine the crop water demand. And then on the other direction, you feed it into a hydrologic model, which then gives you the water availability and tells you what's available for irrigation and what's available to meet the crop water demand. There's been many modelers involved in this, many from universities, University of Alberta, Calgary, and Saskatchewan, and also by a consulting company called WaterSmart, which is the main company that is used by irrigation districts to analyze and to basically put credence into their proposed expansion. The main observations from these studies are as following. Crop water demand will increase, which is I've already mentioned. Summer river flows on their own will decrease. And when I mean on their own, I mean if they don't have added infrastructure such as reservoirs and dams, they will go down. Peak river flow will occur a month earlier by the end of the century, which is quite interesting. And it'll be interesting to see how that affects water management strategies and agriculture strategies and so forth. There is a mixed verdict, in my opinion at least, on the future water availability to support future irrigation expansion. Some tend to be quite pessimistic. The universities tend to be more pessimistic. Others are more optimistic, such as WaterSmart, that work for the irrigation districts. But to be fair, only one model includes the reservoirs, and that's the one done by WaterSmart. So that's important. These need to be included in the model. Also, the predictions are hampered by uncertainties related to climate change, particularly precipitation, but also because of these Pacific decadal oscillations. These oscillations are very, very difficult to predict. And these are different from El Nino and El Nino, which occur on much higher frequency. The PDOs they vary between 15 years to 45 years. Their amplitudes vary considerably, very difficult to predict. So really, to model climate change, it's going to require improvements in modeling with reduced uncertainty. And in my view, this may require collaboration between modelers, workshops, and open source software. Uh, my view on this is that for an issue so important as irrigation expansion, the high cost of the infrastructure, which we're looking at like $6 billion uh, to cover an increase in 30% of irrigation area, and the possible environmental impact, we need to take the modeling very seriously. And really, we need to get the modelers in the same room, comparing their models, discussing them, and discussing how the models can be improved, rather to act completely independently. Also, models developed by irrigation districts through WaterSmart. Not to saying that WaterSmart is not doing good work, but as in any case this important, there must be some very substantial peer review. I'd like to add finally something that came up more recently, which are the Water Act amendments. They came up in 2025, and these amendments, there's some good news and bad news there. The bad news is that a lot of the amendments are there to help consumers take in more water from the rivers, such as applying less strict rules concerning water point of use and diversion, accelerate the project approval process, such as the impact assessment, environment impact assessment, make it easier to transfer water between river basins, and even adjust the definition of river basins, such as combining the Peace Slave with Athabasca river basins. That's been included, and this is, and the indigenous leaders are quite upset about this. On the good news, the amendments strengthen licensing monitor, standardizing water usage monitoring and reporting, apply these to deemed licenses, which is important and means that older license will have to follow this, which was not the case for WCO. And these seem to be addressing some of the concerns that were expressed by the Auditor General in 2024, which was quite critical of the government about how it was establishing, monitoring, and enforcing WCO requirements. So let's get back to the fairy tale. Who is who and what is what? The I think if you look at it, you'll find that obviously the princess is the government. The government is the one making the promises. It has to ideally balance environmental, social, and economic impact and economic concerns. And unfortunately, the promises are what is causing a problem, especially for the Oldman and the Bow River in South Saskatchewan. Licenses were given a long time ago to senior irrigators, and it's very hard to claw those back. Those are written licenses. There's kind of a promise, I guess you could say, is to the river through the WCO, which was a compromise in an attempt to balance these three pillars. And this cannot be met for the Oldman Bow in South Saskatchewan because of the situation of the licenses with senior irrigators. Fortunately, the situation is much different for the Red Deer River. Red Deer River is currently in much better health. Any new irrigation project will involve junior irrigators that will have to follow the WCOs. So the Red Deer River and rivers further north are more promising in terms of having WCOs follow. And who's the king? Well, we are the population. We have a democracy and we have elections. So that's where we stand. So I'd like to end this by just a few thank yous. I want to thank Nature Alberta and Grasslands Naturalists for supporting me in this work and also allowing me to present and giving me a platform to write a detailed report and an article in the magazine. But I really also want to thank Cheryl Bradley from the Southern Alberta Roof-Rate Environment and an informal but very productive irrigation expansion discussion and action group. It involves a wide variety of knowledgeable national, provincial, and local organizations and individuals. This group has made an impact and, in fact, has had an impact on the terms of reference, for example, for environmental impact assessments and so forth. So it's quite interesting how such an informal group but what key players have been able to make an impact. So that is it, and I'm open to any questions.